It is common for any planet to possess a magnetosphere. Fundamentally, a magnetic field is born from a simple induction. The material inside any planet is at constant motion, creating a magnetic field which moves orthogonally to the planet's spin, creating a dynamic action. It is common and almost standard. What is not common is a perfect dipole tilt. The angle between magnetic pole and a normal pole, for reference, Earth has around 10 degrees. Alongside Jupiter, Uranus and Neptune possess a dipole tilt of 50 degrees. Most of the dipole tilts are above zero and are not aligned with the poles, but Saturn has a dipole tilt of 0.07 degrees. This extremely axisymmetric dipole tilt is the result of other observable features and speculations of the interior structures of Saturn. Rain, a very important natural process of water recycling, which brings life into existence on Earth. On Saturn, rain is made out of helium. This phenomenon is a result of immiscibility, which creates a non-homogeneous distribution where most of helium is located deeper into the planet. This creates a stratified collective layer atop of the planet's core, and a helium layer of 0.1 to 0.52 radius could axisymmetrize the magnetic field. Another anomaly on the list is hexagonal cloud in the northern hemisphere. With the radius of Earth's diameter, this atmospheric wonder manages to be perfectly hexagonal. There is also a southern counterpart which fades in comparison. It is nothing like its northern cousin. It is more circular and unstable. Therefore, we can create an accurate model with a sample size of 2 using a northern and southern vortex. In theory, a good single model can simulate both vortices by changing initial conditions. Introducing the rotating shallow water model. By using the cylindrical coordinates and gamma plane on the equations, we can acquire a set of variables such as thickness of the layer, gravity, and Coriolis parameter. Solutions for vortices can give us a zonal velocity of the wind, and we can fit peaks and acquire a set of parameters which are then used to create a more synthetic profile for polar vortices. This is more useful since it removes the noise which comes with the polar vortex distribution and enables a straightforward analysis of possible instability. On Earth, we have a predictable wind pattern across the northern hemisphere. This is called the Rossby wave, which has a certain wave number. After including perturbations in the velocity profile and performing a linear analysis, we can acquire a favorite number of azimuthal wave numbers. And since a Rossby wave creates a standing wave, the wave number shows the number of sides an emerging shape is going to have. Results show that a northern vortex is more likely to create a hexagon, while the southern vortex is more likely to create an octagon. The main difference between the two is the distance from their respective poles. There are two configurations we can use to simulate the hexagon. We can use the jet only or the jet plus vortex modes. The jet only configuration results in a six-sided star with a counterjet at each end with a nominal wave number in ratio of 5 to 7. This results in the intermediate shapes at later stages of simulation. The jet plus vortex configurations assumes that the circumpolar jet is influencing the central vortex. The new configuration shows visually more accurate results where simulations have successfully created a stable hexagon. This behavior was also shown in lab using ink and rotating apparatus. Saturn has two types of aurora, the normal ones and in the shape of the hexagon. The hexagon-shaped aurora stretches along the hexagon boundary and has an abnormal spectral image. This is as a result of upwelling, an accumulation of particles from deeper troposphere caused by the jet. Upwelled particles give a critical data about the interior of the Saturn. The trace particles from lower troposphere get excited around the jet and travel along the boundary. This results in the hexagonal aurora, although a definitive answer is still not available for this phenomenon. The force balancing orbit for Saturn is around 1.6 radius. However, for charged particles this number drops to 1.5 due to Lorentz force. The sharp drop of below 1.5 causes ring rain, where particles fall into Saturn at certain latitudes. Hydrogen particles turn into charged trihydrogens and slowly deplete ring. Most of the particles come from the Enceladus, which is a known water source. Saturn is predicted to lose its rings in hundreds of millions of years.